Welcome to our lesson on eigenvectors and eigenvalues. These concepts are fundamental in linear algebra and have many applications in physics, computer science, data analysis, and more. Today, we'll learn what eigenvectors and eigenvalues are, how to find them using the characteristic equation, and how to diagonalize a matrix. First, let's understand what eigenvectors and eigenvalues actually are. An eigenvector of a square matrix A is a non-zero vector V, such that when A multiplies V, the result is the same vector V, just scaled by a factor lambda. This scaling factor lambda is called the eigenvalue. Mathematically, we can write this as a times V equals lambda times V. Geometrically, this means that when the matrix A transforms the vector V, the resulting vector points in the same direction as the original vector, just stretched or shrunk by the factor lambda. Let's see another example of how this works. Consider a 2 by 2 matrix A. We have a vector V. When A transforms V, the result is lambda times V. Notice that the direction of the vector remains the same. Only the length changes. This is the key property of eigenvectors. Now that we understand what eigenvectors and eigenvalues are, let's learn how to find them. We start with the equation AV equals lambda V. We can rearrange this to get a V minus lambda V equals 0, which we can factor as a minus lambda times I V equals 0, where I is the identity matrix. This is a homogeneous system of linear equations. For a non-zero solution V to exist, the matrix of minus lambda I must be singular, meaning its determinant must be 0. This gives us the characteristic equation. Determinant of a minus lambda I equals 0. Let's work through an example to find eigenvalues and eigenvectors. Consider the matrix A equals 3, 1, 1, 3. The identity matrix I of the same size is 1, 0, 0, 1. So A minus lambda I equals 3 minus lambda n 3 minus lambda. The characteristic equation is the determinant of this matrix equals 0. That's 3 minus lambda times 3 minus lambda minus 1 times 1 equals 0. Simplifying, we get 3 minus lambda squared minus 1 equals 0, or lambda squared minus 6 lambda plus 8 equals 0. This factors as lambda minus 2, lambda minus 4 equals 0, giving us the eigenvalues lambda equals 2 and lambda equals 4. Now that we have our eigenvalues, let's find the corresponding eigenvectors. First, for lambda equals 2, we substitute into a minus lambda I to get 1, 1, 1, 1. We need to find non-zero vectors V such that a minus lambda I V equals 0. This gives us the system x plus y equals 0 and x plus y equals 0. So y equals negative x, and any vector of the form x negative x is an eigenvector. For example, 1 minus 1. Let's verify. A times 1 minus 1 equals 3 times 1 plus 1 times minus 1, 1 times 1 plus 3 times minus 1, which is 2 minus 2, which equals 2 times 1 minus 1. Now for lambda equals 4, a minus lambda I is dash 1, 1, 1, minus 1. This gives us the system. Negative x plus y equals 0, and x minus y equals 0. So y equals x, and any vector of the form x is an eigenvector, for example, 1, 1. Let's verify. A times 1, 1 equals 3 times 1 plus 1 times 1, 1 times 1 plus 3 times 1, which is 4, which equals 4 times 1, 1. Now that we have our eigenvalues and eigenvectors, we can diagonalize our matrix. Diagonalization means finding a matrix P such that P inverse AP equals a diagonal matrix D. The matrix P is formed by using the eigenvectors as columns. So for our example, P equals 1, 1, dash 1, 1. The diagonal matrix D has the eigenvalues on its main diagonal. So D equals 2, 0, 0, 4. Let's verify that P inverse AP equals D. First, we calculate P inverse, which is 1 half minus 1 half, 1 half, 1 half. Then P inverse AP equals 1 half minus 1 half, 1 half, 1 half, times 3, 1, 1, 3, times 1, 1, dash 1, 1. Working through the matrix multiplication, we get 2, 0, 0, which is exactly our diagonal matrix D. This diagonalization is useful because it allows us to easily compute powers of A and understand the behavior of linear transformations. To summarize what we've learned today, eigenvalues and eigenvectors are special values and vectors associated with a square matrix. They satisfy the equation AV equals lambda V. We find eigenvalues by solving the characteristic equation, determinant of a minus lambda I equals 0. Then we find eigenvectors by solving the system a minus lambda I v equals 0 for each eigenvalue. Finally, we can diagonalize a matrix if it has a complete set of linearly independent eigenvectors. These concepts are fundamental in linear algebra and have numerous applications in various fields. Thank you for watching.